what I needed anyway. All right, so we are moving into the last section for chapter 7 that we'd like to talk about. Let's see if I go like this and then get rid of it. There we go. And then I'll do one other thing. If I go like this and bring it back, you're still not doing that. Why? I don't know why it has that shape. I like the other one better, but this is fine. So here we're working with section 7.3, system of linear equations in two variables. So we'll do the best we can with the time, and then again, I'll let you all out on time, and then if I don't finish, I'll just keep recording until I'm done with this section. You're welcome to sit in if you like, but you don't have to. Once we hit the 15-minute mark. Okay, so 7.3 is system of linear equations in two variables. So we're going to be solving a system of equations. A few objectives here. One, we like to decide whether an ordered pair is a solution of a linear system. 2, solve linear systems by graphing. 3, solve linear systems by substitution. 4, solve linear systems by addition. 5, identify systems that do not have exactly one ordered pair solution. 6, solve problems using systems of linear equations, okay? So systems of linear equations and their solutions. Two linear equations are called a system of linear equations or a linear system. A solution to a system of linear equations in two variables is an ordered pair that satisfies both equations in the system. So determine whether 1, 2 is a solution of the system. When x is 1 and y is 2, does it make both equations true? Let me see, that's going to be a 2 minus 6 is -4. That checks out. 2 plus 2 is indeed 4. So the ordered pair 1, 2 works in both equations. So that is a solution of the system. Okay. Okay. So for a system with one solution, the coordinates of the point of intersection of the lines is the system solution, right? So if we have the system of linear equations and we graph these lines, the solution is going to be where these lines intersect or where they cross. Okay. So solve by graphing. I don't really feel like graphing. Yeah, let me not be lazy. Can I paste? Nice. You're still saved. You are awesome. All right. Let me shrink this down some. It's distorting it. Okay. Oh, I didn't realize that. That's good to know. Okay, let's go paper. Let's introduce our graph paper and shrink this down to size. Let me pull my points for reference for later. So I'm gonna get rid of this. Actually, I'm gonna move all this stuff just to use it later. Oop, undo. Okay. Let me shift this. That looks decent. Okay. Let's move this guy. I think if I zoom in, that will help. This guy. Oh no, what did I do? Undo. Whatever. Go. Every time I lift the pen, it jumps. So I'm trying to. There we go. Okay. Okay, those look good. Let me see. So with these guys, let's solve for y in both equations. Let's do. Hey Google, give me a random color.
Green.
She got jokes. Let's eraser. Can I change this color green? Let's go like this. Yeah, that's better. So we'll do this one in green. Let's try that again. Yeah, there we go. Style. Fill is this color. Stroke. We can go like that. It's good. Okay. Now I'm going to copy this. Hey Google, give me a random color.
Okay, I chose blue. It's a very popular color.
I didn't ask for the history of blue. I just wanted the color. Thank you. Let's go here. Okay, so we'll do the first one in green, the second one in blue. Okay, and then let me move this graph because I want to use that for some work. So I'm just going to move this over. That looks decent. Okay, so let's do the first one. Okay, so we started with x plus 2y equals 2. Okay, so if we solve for y, if we subtract x on both sides, we'll have 2y equals negative x plus 2. Divide both sides by 2, y equals a negative 1/2 x plus 1. Okay, so that's the first equation if we solve for y. If we solve for y from the second equation, we're starting with x minus 2y equals 6. If we subtract x on both sides, we have a negative 2y equals negative x plus 6. Divide both sides by negative 2, y equals 1/2 x minus 3. Okay, so we solve for y in both of those equations. I guess I can move this back so it's not so far to the right. About like here looks good. That was decent. Okay, so let's see. For the green, our y-intercept is 1. It has a negative slope. For the blue, our y-intercept is negative 3. So instead of shifting it, which I probably
Don't
should
touch that,
do,
okay, baby?
is everything okay?
What are you doing class at?
Can you guys hear me? Okay, I think it's okay. Let me see. Captions. Yeah, I think we're okay. Let's keep
Yeah.
going. Okay, so I'm going to just change my labels here. So let's see. I think the X's actually we can leave, but I want to change my Y's. Okay. So on the y-axis, I want to go by 2. So negative 2, negative 4, 2, 4. Oh, wait a minute. Okay, I need to reposition these a little bit off. If I go paper, is it this guy? It's not that one. Okay. Let me just manually redo this. We can leave that. Let's get rid of that. And that. Okay. I feel like the x-axis looks decent. Again, this is our positive x. This is our positive y. We wanted to go by 2's here. So 2, 4, 6, 2, 4. Okay. This is a negative 2, negative 4, 2, 4, 6. And this is a negative 1 over here. Okay, that looks decent. So now, if we graph the first one, our y-intercept is a 1. So let me copy and paste this color. Okay. So again, that y-intercept is 1. Okay. And then it has a slope. Copy, paste. It has a slope of a negative 1/2. So then we go down 1 and right by 2. So down 1 and right by 2 puts us here, and we need to connect those with a straight edge. Okay, that's decent. So for instance, when x is 3, 1/2, so a negative 1/2. Oh, okay. What about -3/2? Okay, so what I'll do, let me copy, paste, style. This needs to be green. And I'm just gonna, like this, just drag it into place. About like that. Let me see. When x, let me see, if that's a -1, that's a -3/2. So then 3/4. So 1 3/4. So it's like about here. That's decent. Okay. Let me copy and paste. Style. I want that to be green. Come on. Then this just needs to like about like that. Let me see. That's decent. All right. So we have the first one is graphed, okay? So then the second one in blue, I guess I could just copy and paste, that's fine. Paste. The y-intercept, let's see. The y-intercept is -3. So that's here. And then the slope is a +1/2. So if we, to get to the second point, we go up by 1 and right by 2. Puts us there. And then we connect them with a straight edge. So for instance, when x is 3, that's what, 1.5. Wait a minute. 1.5. That should be negative. Okay. Oh, we might need to extend this some. Yeah, we might need to go to the right by some. Let me see. When x is 4, that's a 2 minus 3 is a -1. So when x is 4, let me see. That would be about here. We would be at -1 here. So it looks like we need to extend our graph so we can see where they cross. That's good. Let me see if I can extend this first one. So it looks like maybe when x is 4. Okay, it looks like they cross when x is 4, right? At 4, what is that? 4 -1. Okay, so we'll confirm. We'll do a test to confirm whether 4 -1 is the solution, right? Because basically the solution is going to be wherever they cross. Okay, get rid of this. Delete. So it looks like it's the point over 4, which is there, a -1, which is about here. Okay, 4 comma -1. So then I'm just going to do a quick check. Okay. So let's test 4 -1. So then 4 plus 2 times -1, that's 2. So that checks out. 4 minus 2 times -1, that becomes a plus, that's a 6. And that checks out, right? So we did have to extend the graph a little bit so we can see where they cross. They ended up crossing at 4 -1. So then the solution to the system is the order pair 4 -1, right? Okay. Oh no, what is going on? Let's go like, nope, that one. Okay, let's go paper. Paper. Let's turn this off. Okay. All right. So that was solving a system by graphing. Let's hang out for like another 10 minutes and then I'll let you go. Okay, let's keep going. All right. So we graph both on the same Cartesian plane. I think they probably used their intercepts, which probably would have been a little bit easier, but that's okay. And they did indeed cross at 4, -1. Okay. All right, we're gonna let that be. So solving a linear system by substitution method. So we saw one case. The first way that we had to solve a system of equations by looking at the graph, but then if your graph isn't like drawn to scale and if it's not done properly, then it can, you may or may not find where they cross, right? So the next technique that we have is called the substitution method. Solving a linear system by substitution, solve either of the equations for one variable in terms of the other. If one of the equations is already in this form, you can skip the step. Substitute the expression found in step 1 into the other. This will result in an equation in one variable. Solve the equation in one variable. Back substitute the value found in step 3 in the equation from step 1. Simplify, and then lastly, check to make sure that your solution works in both equations, right? So the substitution method, what that means is we're going to solve one equation for one variable, and then whatever we get, we're going to plug it into the other equation. At that point, we'll have one equation and one unknown, and we can solve. We solve, then back substitute, then we get our solution to the system, and then check and make sure that it works in both equations, right? So let's see it in action. So we're asked to solve this by substitution. So notice that one of the equations is already solved for y. So then let's take that y and plug it into the second equation, okay? So then we have this 4x minus 3y. We want to plug in for that y. So we're going to replace y with a blank parentheses equals 24. And again, the y that we're substituting is this -x minus 1. Okay. So then from here, we can distribute that -3. Okay. Notice here we have one equation, one unknown, so we can solve. Then we get 4x plus 3x plus 3 equals 24. So what I'm going to do next is isolate my variable. Any term that has an x, I'm going to leave it on the left. Any term that does not have x, I'm going to move to the right, and I'm also going to go ahead and combine my like terms, right? So for instance, 4x plus 3x becomes 7x. And to move that positive 3 to the other side, the inverse operation of plus 3 is minus 3. So if I subtract 3 from both sides, we'll get 21 there. The inverse operation, if we want to isolate the x, if we're going to move that 7, the inverse operation of multiplication is division. So we divide both sides by 7, x equals 3. Okay. So then we use that x to go back and find y. It looks like it's easier to plug this into the first equation. So we'll get y equals -x minus 1, but x is 3 in this case. So then y equals -4. So then our proposed solution to the system is going to be the ordered pair 3, -4. Okay. So then we just want to check and make sure. You still doing that? We just want to make sure that this ordered pair works in our system. Okay. So then, for instance, does -4, is that equal to a -3 minus 1? Yes. If we say what 4 times 3 minus 3 times a -4, does that equal 24? So that's going to be 12 plus 12 equals 24. Yes. Right. So then this ordered pair is a solution to the system because it makes both equations true. Okay, let's hang out for 5 more minutes. Fortunately, I don't have a lot of slides left. Okay, so this is just a typed version of what we experienced. I'll let you go through that on your own. Okay. And then the solution was 3, -4. Okay. So that was a demo on solving the system by substitution. Again, with the substitution method, we solved for one variable, then we took that expression and plugged it into the other equation. At that point, we had one equation, one unknown, so we solved for that unknown. Then we back substituted in to find the other variable, and then check to make sure that our solution worked in both equations. So now here, we're going to solve a system by the addition method. So solving linear systems by addition, that's missing a D, but it's okay. If necessary, rewrite both equations in the form ax plus by equals c. If necessary, multiply either equation or both equations by the appropriate non-zero number so that the sum of the x coefficients or the sum of the y coefficients is 0. I'll come back to that and explain that. Add the equations in step 2. The sum is an equation in one variable. Solve the equation in one variable. Then back substitute, get your solution, and check, right? Okay. Instead of mulling over that, I'm just going to show it in action. And I feel like that's the best way to do this. So we already have these in the form of ax plus by equals c. The goal is you want to get one of the variables to have the same, to be the exact same, the same numbers, but you want them to have opposite signs. So you want one to be positive and one to be negative. I think I am going to eliminate the y because they already have opposite signs. So I could multiply the first row by what? 4. If I multiply the first row by 4, my y's are going to have the same number with opposite signs, and then we're going to add those equations together. Okay. So I'm going to distribute a 4 across this row. Okay. Okay, and I'll write my solution over to the left. So then, what is that? 12x plus 8y equals, let me see, 160 plus 32, so like it's 192. Okay. And then I'm going to bring the second equation down, so that's a 9x minus 8y equals a -24. Now I'm going to add these two equations together. Okay. So when I do this, because my y values, the whole point was we wanted y to have the same coefficients with opposite signs. A number plus its opposite, these guys add to 0. So then 12 plus 9 is what? 21x equals, if that was a 12, that would be what? An 8, 6, 168. Let me see. 92, 72, 70, 68. Okay. What is that? Is that an 8? 168, yeah. So if you divide both sides by 21, x equals 8. Okay. So then we can use this, plug it into either of the original equations to solve for y. I'm going to plug it into the first equation because the numbers look smaller and easier to work with. So if x is 8, 8 times 3, that's going to be what? 24 plus 2y equals 48. I'll continue working over here. Subtract 24 from both sides. Then 2y equals, what is that, a 424? Divide both sides by 2, y equals 12. Okay. Okay, see the time. So then our claim is that the solution to the system is going to be the order pair 8, 12. Okay. Copy. Let me see. 24 plus 24 is indeed 48. 72, let's see, what is that? 80 plus 16 is 96. 72 minus 96. 72 and 96. 72, 82, 92. 24, -24, right? So this order pair makes both equations true, so this is indeed the solution. Okay, this is just the type version of what we just experienced. Okay, I do want to mention this. A linear system having no solution or infinitely many solutions. The number of solutions to a system of 2 linear equations and 2 variables is given by one of the following. We could have exactly one ordered pair solution that's going to show up like in the image on the left where they cross at one point. The two lines intersect at one point. Another type of solution that we get sometimes is no solution. That occurs when we have two non-vertical parallel lines. So when we have two lines that have the same slope with different y-intercepts, they never cross, so there's no solution. The lines are parallel. And then infinitely many solutions occurs when two lines are identical. That usually occurs when one line is a multiple of the other. Right, and then that means that one line is on top of the other line, and so there are infinitely many solutions. Okay, we have an official 5 minutes, so let me just because we're almost done here as well. Solve the system. Okay, we got 10 slides. So I'll do this. We'll put a pin right here. I'm going to go ahead and release everybody, and then I'll finish this out. You don't have to stay on the recording. As far as announcements, I think the main thing on My Open Math is exam 1 is available. It's due next week sometime. I think maybe on Tuesday at the start of class. But the due date is there, right? Uh, as usual, with all of our assignments, we get unlimited attempts. And there's only, well, with going forward right now, I think there's like a 10% late penalty for anything after chapter 3. Okay. So if there aren't, are there any burning questions from you all going once, twice? Okay. So if there aren't any burning questions, I'm going to let you all go, and I'm going to go ahead and finish out these last couple of examples just for the recording. You can watch it at your leisure. Either you're welcome to stay on a call right now, or you can watch it later in the recording if you want. Okay. All right. All right. Have a good weekend, and I'll see you all next week. Okay. So let's solve this system. I think I'm actually going to start. Let me start by getting a copy of the original. We have this 4x plus 6y. I'm just grateful that it's like not a whole slew of slides, right? It's only a few slides. And then we got this 6x plus 9y equals 12. Like, I'm not going to lie, for like the past couple of days, I was getting my mind right. Like, okay, you got to be ready to stay for like X amount of time. But these were quick. I was like, praise the Lord. Okay. So now, in order to do the elimination method, we want to get one of the variables that have the same number with opposite signs. All right, so we want to find the least common multiple. I think I'm going to cancel the x because it looks like those might be easier to work with. So, like for instance, the least common multiple between 4 and 6. So if I start with the larger number, which is 6, notice that 6 is not a multiple of 4. So then I say 6 times 2, I double it. So then 12 is a multiple of 6, 12 is a multiple of 4, so then 12 is the least common multiple, right? So I want to get both of those numbers to be 12 with opposite signs. So I'm going to multiply the top by 3. I'm going to distribute a 3 across these guys. And for the bottom, I'm going to multiply by negative 2. I'm going to distribute a negative 2 across these guys. Okay. So if we account for those changes on top, we get what? 12x. 6 times 3 is what? 18y. And that's 36. On bottom, that's a negative 12x. That was the goal. Minus 18y. Now that's a little bit of a hiccup. And then we get a negative 24, right? So then if we add these together, not only does the x cancel, but the y cancels as well. They both just happen to cancel. So then we get 0 on the left. What is that? 6 and 6 is 12. And we get 12 on the right. Notice that this is a false statement. This is false. So because our variables, all the variables canceled, and we finished with the false statement, that means that these lines are parallel. So there's no solution here. This is an example of something that's no solution. Okay. So in other words, these lines are going to be parallel. They should have the same slope with different y-intercepts. Okay. So it should be no solution. Let's copy. Okay. And you see it here. And we do capture the no solution with the symbol. This is called the empty set. It's a 0 with a slash through it. So we say it's the empty set or no solution. Okay. Okay. We're almost there. So let's solve this system. So they've already solved for one equation. They've already isolated one of the variables. So I think I'm going to use the substitution method here instead of elimination method. So we'll substitute the first equation into the second, and we're going to get 15x minus 5 times y equals 10, but then our y equals 3x minus 2. At this point, we have one equation, one unknown, and we can solve. Let's distribute this negative 5. We get 15x minus 15x plus 10 equals 10. If we combine like terms and set it to 0, ultimately we'll get 0 equals 0, which is a true statement, right? So this is because all the variables cancel and we finish with the true statement. That means we have infinitely many solutions. That means that one equation is a multiple of the other. And so our solutions, we have infinitely many solutions, and the way we capture that, all solutions are going to take on the following form. No matter what x value we choose, the corresponding y is going to take on the form 3x minus 2, right? So if you choose your favorite x value, so you can generate an infinite number of points with this little setup, right? I'll generate a few of them to show you that it works. Hey, Google, give me a random number.
Here's a random number, 4.
4, right? So when x is 4, the corresponding y is what? 10. So then if we use this order pair in the original, it should be true. 12 minus 2 is indeed 10. 60 minus 50 is indeed 10, right? So it checks out. Let's do another one. Hey, Google, give me a random number.
Here's a random number, 86.
Oh, come on. You're making this difficult. So when x is 86, that's my fault. You know, I should have specified, but I didn't want to specify. Okay. Let's do this. So 8 times 3 is 240. 240 plus 18 is 256. So then 252, right? Okay. Let's see if we can confirm. Hey Google, what's 3 times 86 minus 2?
3 times 86 minus 2 is 256.
Okay, maybe that's supposed to be a 256. I think I probably did my calculation wrong. We'll do a 6 there. Okay. Hey Google, what's 15 times 86 minus 5 times 256?
15 times 86 minus 5 times 256 is 10.
Right? So again, this isn't because all the variables cancel and we finish with the true statement. That means that we have infinitely many solutions, and they all take on the form, no matter what x you choose, the corresponding y is going to be that 3x minus 2. And then you can just choose a few values of x, find the corresponding y, and then test those solutions in the original to make sure that it works, right? So these are just some test values. I'll do those in purple, and I'll call them test values. So these are just test values. Okay. And then we want these guys to be in purple style, purple. Cool beans. Okay. We're almost there. Party is almost over. Bummer. What? We're almost there. Party's almost over. What a bummer. Right? That's from P90X. I don't know if you guys ever use that or not, but that's Tony Horton would always say that. So it periodically surfaces in my psyche. Okay. So here's a type version of what we just experienced. I'm gonna just kind of let you go through that. Let's see. So modeling with systems of equations, making money and losing it. Revenue and cost function. A company produces and sells X units of a product. The revenue function is the price per unit sold, which is our X. Our cost function is our fixed cost plus the cost per unit produced. And then the point of intersection of the graphs of the revenue and the cost function is called the break-even point, right? So when we're modeling with like money, you know, revenue is the money generated from the business. The cost is the money you have to spend to run the business. Profit is going to be revenue minus cost. where the revenue function crosses the cost function is the break-even point. So then we can get a sense of, what's the minimum we need to produce and sell in order to turn a profit, right? These kind of things. Okay. So a company is planning to manufacture radically different wheelchairs. Fixed cost will be $500,000, and it'll cost $400 to produce each wheelchair. Each wheelchair will be sold for $600. Write a cost function C for producing X wheelchairs. Matter of fact, we can do that. We can do that rather quickly. Our cost function is going to be our fixed cost, which is the 500,000 plus the variable cost. So we're going to say 400 times each wheelchair plus a fixed cost of 500,000. Okay. Write the revenue function from the sale. So then our revenue function, if we're gonna sell it for 600, we're gonna generate $600 for each wheelchair that we sell. So if we sell one wheelchair, we get 600. If we sell two, it's 1,200. 3, 18, so on and so on and so on. Determine the break-even point. Describe what this means. So basically, they're asking us to set the revenue function equal to the cost function and then solve for X. So if we say R equal to C, because I'm short on space, I'm going to just kind of abbreviate here. I'm going to subtract 400 from both sides. So at some point, I'm going to get 200X equals 500,000. So then ultimately, we'll get, if we divide by 200, X equals, it's going to be, what is that, 5,000? 5,000 divided by 2, 2,500 units. So we need to produce and sell 2,500 units. When we produce and sell 2,500 units, that's going to be break even. Once we sell the next one after that, that's when we start turning a profit. So anything above 2,500 is going to be profit. But as long as we produce and sell less than 2,500, we're still in the red. We haven't earned our money back yet. So that's the break even point. Okay, let me highlight this. Or I guess I can just copy and paste. I'll just use these. This is what we got for part A. You have to forgive me. I'm just like eager to start my weekend. I kind of work throughout the week so that I can like do whatever I wanted to do on the weekend, and I'll just pick everything up next week. Okay, so this is what we got. Let's look at our prepared notes. So we got our cost function. I think we got that same thing. We got our revenue function. Okay, cost of revenue. That's fine. So then if we equate the revenue function with the cost function, the break-even point is 2,500 units. And then, so if we plug this into the revenue function, that tells us the amount of money that's going to be generated if we produce and sell 2,500 units. Man, so it's going to cost us 1.5 million to produce it, and we don't break even until we produce and sell 2,500 units. Okay. This means that the company will break even if it produces and sells 2,500 wheelchairs for $1.5 million. So then anything above that, once we start producing and selling more than 2,500 units, that's when we start to turn a profit. So notice here, if we were to graph these two, on the left, that red portion we're still in the red. We haven't made our money back yet. Not until we get, I would have made that green, but we'll get on the other side of that cross here where we start to get in our profit. Then the next thing is once we start turning a profit, now we see, okay, what does it take to maximize the profit? Like, what are the limits? What are people willing to pay for this item? If it costs us like $400 for each wheelchair, are people willing to pay $800, $1,000, 20? Like how much? How much are people willing to pay? How much revenue can we generate, and is it possible for us to maximize this profit? Right. This kind of discussion is actually like the precursor to things that I used to study in like grad school. I was studying like applied mathematics. All right, I'm about to feed you. My dog is like, she's doing things to say I'm hungry. It's time. It's lunchtime, right? This is usually when I feed her. So anyway, but yeah, okay. Let's see. So the profit generating after producing and selling X unit is basically going to be the revenue minus the cost, right? So the profit function, if we say the revenue function minus the cost function, you see it there. So then if we look at the profit function, when the profit function is negative, we're in the red and we haven't made our money back. When our profit is zero, that's our break-even point. And then anything above the x-axis is the amount of profit that we have. Okay. Are there any burning questions? All right. So I didn't go that much over. Any burning questions going once, twice? Forever hold your peas and rice. Okay. Yeah. So you guys are awesome. Thank you for staying. Again, exam 1 is available. Pretty much, if you just complete the assignments on my open math, that's enough for me. Um, and then we'll meet next week, same time, same place. And on that note, we're going to end the session here. And from one beautiful mind to another, have a great weekend, ladies and gentlemen.
Have a
Until
good
next
day.
time, take care. Peace.
Have a good one.
You as well.
Have a good one.
You too. I think that's the right folder. I mean, she is like chowing down over there like she has never eaten before. We go feed this pooch. Stop. All right, let's end the reading for all.